We talked about producer-consumer queue last week. Thought it was an interesting introduction into multi-threading, but I wanted to give you a deeper dive into multi-threading and show you how some of the multi-threading components are actually designed and implemented, how they work on the inside, under the hood. We've all used mutexes or semaphores, maybe even spinlocks if we've done some kernel programming, or event objects on Windows. But have you ever wondered how exactly those work, and how would you implement one if you were writing an operating system or a library for the C++ compiler? How would you implement those things? So that's what I want to cover today. So let's start with simple things. First, I must include, excuse me, let's include something else. Include atomic. There you go. Without it, we wouldn't get far. So let's start by implementing a simple spinlock. And what is a spinlock? It's a mutex, effectively, for mutual exclusion, but it is very, very primitive. It relies on an atomic variable, meaning a variable that when it is modified atomically. I know, I didn't really say much. Meaning that if one thread is trying to read this variable, the other thread will never see an intermediate state. Let's say this variable is a 64-bit int. If it wasn't atomic, it would be possible that one thread trying to set this variable to some value, while another thread would be trying to read it. There'll be a data race, and this thread that's reading it could actually see this variable set in some intermediate state, right? When the memory of it was, let's say, the first 32 bits were set, but not the second, and so on. So that's not atomic. Atomic variables, you don't have this problem. And the only reason why we have them, frankly, is because there's hardware support for it, as far as I understand. There are things like atomic operations on the CPU, things like compare, swap, exchange, that operate on simple values. And from those, we can build all the way up to multi-threaded, multiple producer, multiple consumer queues, and all the different synchronization primitives I mentioned. But let's start simple. Let's write a spinlock. Spinlock. There we go. Public, private. And what we want this spinlock to do is just have two functions: void, lock, right? And unlock. Void, unlock. I won't get into things like try lock or try lock while waiting for a specific amount of time. That would get we will go down the rabbit hole and we wouldn't come out today, at least. So let's keep this simple. And in order to do this, I need something called atomic flag. And let me demonstrate what atomic flag is and how it works. Atomic flag. There, atomic flag. Let's go A. And you must initialize it to atomic flag init. There. It has to start in this state, according to the language rules. That is nothing more than just that. False. But nevertheless, you should prefer this. So what can you do with an atomic flag? Just look at the methods it has. Not very many. Look at that. Constructor, destructor, and then two methods: clear and test and set. So that doesn't look very useful, right? But let's see what they do. Clear, I think that's pretty obvious, right? This atomic flag, it can have two states, by the way, not to mention. I think that's obvious, right? It has true or false. That's it. So clear resets this atomic flag to false, to 0. Now, test and set, on the other hand, returns a Boolean. And what it does, it atomically sets this variable to true and returns the previous value. So it does, it's a load and store operations, right? It loads its value, gives it back to you, and at the same time it stores some new value in it. So the fact that this is atomic, and the fact that it tells us what the value was, and we know what the value will be, is very useful, and I'll demonstrate why. So let's have this spinlock. It will have this flag. Let's call it m underscore flag. So I would like to call my member variables m underscore and then blah blah blah. Okay. So unlock. Let's start with unlock. Right? Unlock is easy. Flag or m. Come on. M flag that clear. Okay. And let's assume that this mutex, when it is the spinlock, when it is constructed, it is not locked. Its initial state is unlocked. So the m flag, should we choose true or false to express this state, is the question, right? And we know that we cannot even read its value. We can test and set, and that's kind enough to tell us the previous value. And by the nature of the function, we'll know what the new value will be. So let's say that the spinlock is locked when m flag is set to true, and it is unlocked when it is set to false. So we can only take the lock and change its value when it is unlocked, meaning when its value is false. So how could we do this? We go m flag and we do test and set. How can we lock it, right? What we need to remember is that if this variable was set to true, that means it was already locked by someone else. And since it's a spin lock, we will spin. So we will do a while loop, and in this while loop, we will just keep looking and setting this variable. So test and set, and nothing more. And the idea here is that if it is locked by somebody else, that means that its value is 1, so this loop will keep spinning. And test and set will return the previous value and then set it to true, which in our case it's a no-op because it's already true. So we can freely do this in a loop without changing its state until it is set to 0. So when somebody else clears it, then when there's a thread waiting in this lock, in this loop, it will suddenly break out of this loop because it will see, the previous value was false. So this loop will stop. And at the same time, the current value will be set to true. So breaking out of this loop is equivalent to acquiring the lock. So let's see if this works. Let's make 2 spin locks, S1, S2. And let's write a simple example with 2 threads that try to print A, B, A, B, A, B to the console, and they need to do it without stepping on each other. So let's create thread 1. Let's take reference to these spin locks. And thread 1 will, let's see, let's put it in a loop. It will what? It's one lock isn't enough for this, by the way, right? If it just takes lock, then prints A, and then unlock, well, that's going to work. And if I create a second thread, let's see, detach on this one, and on the second thread, I'll do the same thing. And if I did this, thread, let's call it D. This one's going to be printing D. So what's going to be the output here? It's going to be printing A and B. But we have no guarantee to know what order. It may print 5 A's and then 10 B's, right? We don't know. And let's in fact run it from the console. Xcode bin, come on, bin, debug. Here, what do we have here? Okay, playground. Nothing happened. Oh, I detached, that's right. This one I need to join. I will never join it, but that means that it will run forever. Okay. Here. And what we get? We get AB, 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 AB. But look, this series of A's. So that's not good. So let's use the second log. And let's say, how could we do this? Ideas? I remember Todd asked me this question at an interview actually 3 years ago. I remember needing 2 logs. Like 1, 2. Whatever. I can't think of this right now. But it looks like our spinlock is working. And let's in fact let's do this. 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's print a lot of these. And if it wasn't working, these printouts, let's see, let's do 10, 20, 50, and then a new line. Right? If we did this without locking, these long strings would interleave, and I'll show you. 10, and then we're going to do 50 of this, right? There. Click on this. Let's first run it without locking anything. There, if I build it and have these 2 threads go, you will see that, well, you may see, they should at some point here. That happened here, for example. Print it twice, or maybe that's a new line. Let's see. There should be a spot somewhere where they print over each other. Or we may just be getting lucky. But as you can see, they are unsynchronized. Yeah, we may just be getting lucky here. Maybe if we drop the new lines, it will be easier to see that they are in fact stepping on each other. Let's try it. We're not synchronizing them one bit. Let's see. Can you see this? No. Well, you're just gonna have to take my word for it. They would be stepping on each other. So now that we have this log, let's see. Let's say let's say second thread never unlocks, right? So we should see this one, maybe print once, and then it's going to unlock. Then it's going to try to lock again, but then the second thread will lock and it will never release this lock. So it will only be printing B's. So I think I need to build it for it to happen. This one lock. Yeah, and they're stuck. Interesting. It shouldn't be. Lock. That's right, because lock. Right, lock blocks. Silly me. I'm in a while. So let's lock it outside of the loop. and never unlock it, while this one tried to lock and unlock it. And what we should see here is it will initially probably print some A's, and then it's all B's all the way down. The other thread has been starved out completely. Let's see. Can you see some of this? Oh, almost. Past it. Here we go. Got a B, we got some A's. No, I'm looking at the wrong output, I think. Well, in any case, it has been starved. So our lock works. All right, enough of this silliness with printing. So that's a spin lock. It is, you may wonder, well, why would I use a spin lock, right? It spins, it's inefficient, it's in a loop. Well, in some places, that is the only synchronization primitive you may have access to. For example, in kernel, if you're programming in Windows kernel, there is something called IRQ levels, and different things can happen on different levels. And the purpose, among other things, is to block certain things from happening while more important things happen, like interrupts come in and so on. At a certain IRQ level in kernel, you may not use any sort of events or mutexes. The only thing you have is a spin lock. So this is in fact quite useful. There is a more advanced part to this, and that has to do with C++ memory model and memory ordering. And you can pass these additional arguments here, like memory order acquire, for example. I'll explain what this is in a bit. Here to do this properly, you would do memory order release. It's not necessary. It has to do with the compiler rearranging reads and writes. If you have few atomic variables, let's just assume they are atomic, and you do things with them. Say this, C equals X. You don't really know whether or not this is going to happen in the same order. The program's output will look as if it happened in source code order. That's a promise the compiler makes, but the compiler is free to rearrange those things, and sometimes that's a bad thing. Sometimes we don't want this. So these memory order, the acquires, releases. There's another one for sequential consistency, acquire, release, and so on, or relaxed. It creates sort of barriers in code, and it says that no read or write that happens before this line can be reordered to happen after this line. So nothing above can cross down past acquire, and release does the opposite. Nothing that happens after release can be optimized and rearranged by the compiler to cross up effectively. And this on some architectures can give you a significant performance boost if you acquire atomic variables with this in mind, because if you don't, the compiler will be forced to maybe put fences and so on, which is something that's forcing complete cache synchronization between different cores, whereas this may help you gain performance. I think on x86 or x64 on Intel's, it doesn't matter. It's done in such a way that there's no performance gain from it. But I think on ARM and other chips there is. So anyway, so this is our spin lock. What's next? Next, I have a few other primitives in mind. Let me look up that list again. Okay, spinlock, event, semaphore. All right, so let's think about an event. We've all used them, I think. Windows provides us an API, right? In Windows, you can type create event and so on, a bunch of options. Among those options, there are things like auto resetting event or manual event, event's initial state. What do those things mean? So let's start with a simple manual event. What manual event means is that once it is signaled, any thread waiting on this event, and any future thread that may wait on this event will be unblocked immediately. So this event will remain signaled for as long or until you actually reset it manually. Whereas a automatic event, once it is signaled, it will only pass one thread through, and afterwards, once it let a single thread be unblocked, it then resets itself back to a not signaled state. They're also very useful things. If you want to say synchronize a pool of threads and you want them to do something and then all of them need to wait, and then at some point when you want to release them all, you could do that with a manual event. Have them all wait on this event and then signal it once, and all the threads that are waiting or will try to wait will be immediately released from waiting, unblocked. And auto event is useful for things like producers, consumers. So you can have an event and signal to another thread that something is available, and then with another event that other thread, the consumer thread, can signal back to you that it's done with it. And that's actually, now that I think about it, this spinlock example that I was about to write, it actually so it can print A B A B A B. It actually needs events. I was wrong. I thought it needed spinlocks, but we can do it in a bit once we have an event class. So let's start with a manual event. Manual event. And again, we'll keep things simple. Public, private. We will have a very simple interface, but let's create a constructor which allows us to explicit bool state. It tells us whether it's signaled or not. Let's default it to false. It's a reasonable default for an event. And m signaled will be initialized to state. That's it. So let's have this variable here, boolean. And notice it doesn't have to be atomic. And that is because we don't need this. That is because this variable will be always used around a mutex and a condition variable and locks and unlocks. And these are complete memory fences, I think they're called. Meaning these events happen after all the caches have been synchronized across all cores. So it is safe to keep this boolean non-atomic, because we will always, when we need to read it, we will always read its true value. And we will be doing this exclusively. So there will be no two threads trying. Okay, and to implement this, besides this signal state, we will need a mutex. Let's call it mutex, and a condition variable. And we could actually later use this spinlock to do it. Maybe we'll do it in a bit. There's condition variable and there's condition variable any, and that allows you to its wait function accepts a more relaxed STD unique lock. Condition variable wait function requires a STD unique lock that's holding an STD mutex, but condition variable any will accept any unique lock that holds anything that's lockable, right? It's a concept. In order to be lockable, you need to implement lock and unlock methods. That's it. Okay, so and mutex and condition variable. Okay, so let's start again. Let's start simple. Void signal. There. How do you signal this event? Well, you need a lock, most likely, since we have this mutex, right? We want to protect this signal variable. So let's do std block. There, block. Let's call it guard of mutex. Okay, so now we have a lock. Then signal. So let's mark it as signal. So set it to true. Right, we required a lock, so we protected this variable. Then we exit this this scope, and we signaled it. We signaled it once, but because this is a manual event, you want to unblock all possible threads that may be waiting. There may be more than one. So here, condition variable, we want to notify all. We don't know how many there are. If we do notify one, well, that would only unblock one. And that will come handy when we're building a auto reset event. But for a manual event, we want to notify. Okay, so that's signal. And then wait. How do we implement waiting on this event? Easy peasy, we're going to do a loop, right? Like we did, well, not exactly a loop, but a condition variable with a predicate. So it internally kind of acts like it's working in a loop. std. Here we need unique lock, because we'll be passing this to condition variable. So let's lock this mutex, and then let's wait on the condition variable, like we did before with the queues, guard, and then the predicate is pass our response. So this predicate tells us, right, is this condition variable ready to be unblocked from waiting? If it returns true, then it unblocks. So it can simply return signal. There. If signaled is set to true, then this wait will unblock. And remember, this wait with a predicate is implemented in sort of like this. So while not predicate, right? So while this predicate returns false, let's unlock the mutex and wait or sleep or whatever. And then once we're signaled, right, it wakes up and atomically acquires the mutex, then spins back around, checks if this predicate now returns true. It does, because it's a bang true, right? We get a false, it breaks out of this loop, and it already has the mutex blocked. So that's how this works. Okay, so let's see. I can write a little test program. So this is manual event. Manual event, let's call it E1. Let's create a whole bunch of threads. And then we're going to signal all of them that they're ready to go. So let's say 4. Let's create 10 threads. And we will take this event by reference. No parameters are needed for this thread. And what we will do is E1 that wait. We'll wait for this event to be signaled, and then we'll print something. Let's say, I don't know. Well, actually, let's take a parameter. Int x. Let's print this x that we are passed, and we will pass the x will be I, right? And then dash. Simple. This isn't production quality code, of course. Don't do this at home. But I just need to quickly create some threads and detach them. So I'm creating threads with this lambda. It takes by reference, so it can use this event, and it's given a parameter. which will be the value of I in this loop. Let's maybe do this. And once the event is signaled, it will print it and exit. So now in the main thread, let's say, let's print out more. Say starting I, and then let's keep it this short sleep. This thread, this thread, 4, 10 milliseconds enough. It just so it prints these starting things nicely. I think I need chrono for that. Chrono, and I need namespace std chrono to get these unit roles. I have to be able to write 10 ms. Let's see this thread. Unexpected namespace, name this thread. No, it's not an unexpected. Oh, we've been here before. Std this thread. Sorry. Okay. No. This thread. Why do I keep running into this issue? Anyway, this thread, sleep 4. So the main thread will sleep for 1 second. Or actually, sleep for 3. That will be a while, and then once we're done with the sleeping, P1, we will signal this event, maybe sleep some more, so the other threads have a chance to be unblocked and print and such. Let's see. Signal. Yep, that looks okay. And here, this thread, sleep 4, 20 seconds. So let's give them a short delay. So everyone follows what I'm doing, right? Starting 10 threads. They're going to start. They're going to print that they're starting. Print their number. Let's see. This wait, actually, it's not the right place for this wait. I need to create these threads not at the same time. So we'll do this inside the for loop. So I'll create a thread, give it a chance to print something, wait, say 100 milliseconds, and then repeat. Create 10 threads. It'll start. It'll be waiting on the event. Once it's signal, it will print and exit. And the main thread will wait for 3 seconds, signal, and then wait for 1 more second. So let's see if this works. So we should see in the first second, they will print starting 1 through 10. Then 2 seconds later, they should all be unblocked and it will print just the number. So let's see. Starting 1, 2, there. And they, of course, they printed all over each other, right? Because of lack of synchronization. But the event works, right? I signal it once, it unblocked all 10 threads. Let's see, let's try this again. So 3 seconds, 1 second. Let's put this. There, starting 1 to 10, and then they get all unblocked at the same time. So good. So manual event works. Let's now implement a automatic event. Some spaces here. So very similar. Class, let's call it auto event. And on my blog and on my GitHub, I have more complete implementations of these. If you're interested to see how other methods like wait for, wait until, and so on can be done, it's all there. But I want for the sake of time, I will not go over all of those. Public again, private again, we can, the same variables will be needed. So I'm just going to copy and paste them here. And same methods, right? We want a signal, void signal, and we want another void wait, right? Except this time we want the event, the auto event, to get back to its non-signal state after it has woken up one thread, or after, if there is no thread waiting, so after some thread eventually got to a wait, got through it, and then it reset this event back to a not signaled state. So again, same constructor. I'm making them explicit, right? So if you ever, I don't know why you would, but if you ever pass this event, try to pass it by a const reference or something, or by value to a function, you will have to spell that out explicitly, right? You cannot then call this function with, like, say, true, and it would use the user-defined conversion, use this constructor. That would be messy. If your code is invisibly converting true and false into event objects, it's safe to say you're doing something wrong and or unsafe. Okay, so signal. Signal is, for the most part, identical. So we still need to take a log. We still need to signal this. However, this time, we only want to wake up one thread if there's one wait. So notify one, right? In the manual event, we did notify all. In the automatic event, signal notifies only one. Okay, now what about the wait? We probably need to do something similar in the wait, but that's not all. Right, so if it's signaled, it may or may not wake up one, but it will remain signaled. And then if another thread enters here, it will acquire this log, and then it will try to wait on this condition variable until it is signaled. And it will be signaled at this point if this code here was already executed. So then one last thing it needs to do, since it has the lock, right? Once the wait unblocks, we are holding the lock. So now we need to reset it back. So here, that's the extra thing we need to do. And the difference really is, or all it really comes down to is to notify all versus notify one. And then in the wait state, may be somewhat counterintuitive, but once you are unblocked from the wait, that means the event has been signaled. That means that thread waiting on it is unblocked. It then immediately resets it back to false. So let's see if this works. And let's see if we can now implement this problem that I had in mind earlier, right? When you have two threads printing A, B, A, B, A, B, A, B. So let's comment this out for a second. And for this, we will need two events. So thread one this Xcode IntelliSense is going to drive me nuts one day. So the first thread will be spinning in a loop. And the first thread, let's say, will be waiting for event one to be signaled. So once event one has been signaled, it will then wake up. It will print A. And then, see what happens then. I'll get there in a moment. So let's detach this thread. And the second thread will do something similar, except the second thread will wait on event 2, and then it will print B. And this one can also detach. And here eventually we have event 1 and event 2. So let's start with E1. We'll signal E1. Except they need to be automatic, right? Not manual events. auto event 1, 2. Let's call it automatic event. So there, automatic event 1, automatic event 2. We'll start with 1, but that's not all, right? After thread 1 has been signaled and prints something, the automatic event is reset until it's signaled again, but then it needs to tell the other guy, hey, I'm done, now it's your turn. So it signals this second event, and now this thread is unblocked. So it signals this event and then goes back around this loop and waits on the first event, right? So but the second thread is unblocked, it does its thing, and then it notifies back to the first thread that, all right, now it's your turn. So see, you need 2 events for this. You have 2 events for 2 threads. 1 event per thread to be unblocked, and then they wait on one and notify the other. So if we start with signaling event 1, and then let's say sleep for a bit. Let's just give it a second. The first thing that will be printed will be A. Let's actually skip this new line. So it will be clear to see that they are really not stepping on each other. There. So if we signal automatic event 1, this will be the first thread, so it will start with A and then B. Let's see. There you go. We're printing A, B, A, B, A, B, A, B, and notice they are in perfect harmony, perfect order. Let's see if I can find the beginning of this. This will be let's find it. So I can show you that it in fact started with A. There, right? A was the first thing it printed because we notified automatic event 1 first. Let's actually give this. Let's just give that a millisecond. But if we signal the second event first, then it will start with a B. There. Good, millisecond was enough. See, it started with a B, and then it's interleaving. Again, if we start first event, now it starts with an A. So there, these are event objects. And you can implement them using primitives like a mutex and a condition variable. I promised you that we could use our spinlock here inside this event in place of the standard mutex. So let's do that. So instead, and I wouldn't recommend using a spinlock for something like this, but for the sake of exercise, we will do it. So here, spinlock, we call it M mutex, right? It starts off as not signaled. Now this is problematic with this unique lock because this condition variable wants a unique lock with a mutex. But I mentioned earlier that if you do unique variable, condition variable any, then it's now okay. So there. Now this builds. Let's comment out this code. Wait for a second. And now the behavior should be the same, right? It should still print AB, AB, AB because it's using these auto event objects. Where are they? Here. But instead, it's using our spinlock. So, like I mentioned earlier, sometimes in kernel programming, there are circumstances where you can only use spinlocks. And here, and I'm not sure about condition variables, so don't quote me on that, but they may just be some sort of an atomic. I don't know. Or they may be a OS internal structure primitive that's created for you. I'm not sure. But it's likely that starting with a spinlock, you can then, in these circumstances, in kernel, and these dispatch levels, you can then implement yourself events. Okay, let's see. It's still going to work with our spinlock. There. Segmentation fault. Not sure why. Well, I think I know why. we're not exiting those threads cleanly. There's something going on there. But anyway, yeah, this our spinlock can be used here in place of the mutex. So let me just make a copy of this. So if we're using a standard mutex, we're using a standard condition variable. If we want to use our spinlock, we need to do so here. You can use your spinlock instead. There. So let's see. We got spinlock, we got manual event, automatic event. Let's now see if we could implement a semaphore. Let's see here. Unless I missed another primitive, I don't think I did. I have some fast mutexes, fast read-write mutexes. They were designed by Alexander Terekhov, I think, guy who did most of the pthreads work on Unix back in the day. But I won't get into those. Let's see, we got a spinlock, we got an event. Okay, let's do a semaphore now. So what is a semaphore, right? It's kind of like a counting mutex. It can be, or counting event. It can be signaled, or it can be posted, it can be waited on, and it has a count. And let's say you start a semaphore with a count of 3, then if 3 threads try to wait on the semaphore, then all 3 will be able to pass through the semaphore's wait call, but the 4th one will then block until somebody posts the semaphore, meaning until somebody increases its count above 0, right? So class semaphore again. We'll start with a constructor and signed in. So let's say this would be count. Its initial count. We can default it to 0. It's fine. So that's it. That's a unposted semaphore. Let's see, count. There we go. We'll need some variables, and then we want to have 2 methods. So let's call post. So this will increase the count on the semaphore. And let's do wait. So this will block if the semaphore's value has fallen down to 0. And if it has not, then this wait will let a thread through while decrementing the count on the semaphore. Signed in. There. So what would we need? Again, we'll need a mutex and a condition variable. These are great. You can build so many cool things with them. So post. What would the post do? Again, it would first acquire the mutex. Scope block here. Since we will not be passing it to a condition variable in this method. And mutex. Okay, so we have the lock now on the semaphore. And simple m count. We're just going to increase it, right? Or clearer and count will be m count plus 1. So we do that in a protected section, and since we incremented it by 1, we have potentially only unblocked 1 thread, or we will, so we notify 1. There, so that's our post method. And in wait, similarly, unique lock stored and mutex, and then this variable will wait. And what will be our predicate? We want to wait, or we want to unblock if count is not 0, right? So if the semaphore still has a greater than 0 count, we do not want to wait. We want to get through this wait statement. So if m count is greater than 0, right, then it will return true. So we will not end up waiting. And then finally, because we got through, we have to now m count equals m count minus 1, right? So we decrement. Now, I'm sure you are aware there are methods. You can increment a semaphore by more than just one. So let's add this method. So you can have another post, unsigned int, count, and in this method, this post will allow us to bump the semaphore up by not just by 1, but by a greater than 1 value. So that could potentially unblock more than one thread. So we need to wake up all of them. Or you could refactor these two methods into one. So let's see, let's try that maybe. So instead of these two, you can just create one count, which will now be defaulted to 1. Then go to the same. And then here, if count was 1, then you notify 1. Else, if count was greater than 1, notify 1. There, you want to. Of course, put a check in there. Make sure nobody's doing 0. It's kind of silly. Acquiring this lock and not changing this count. Just a waste of CPU cycles. Okay. So let's see if we can test this. And how could we test? The semaphore? How about we will create a minus semaphore. There. Why is it not liking my syntax? Semaphore, public, private. Bada boom, bada bing. Everything looks good here. Alright, semaphore. Let's call it sem1. Let's see if it still builds. Yep, we're good. Okay, so let's initialize the semaphore to, let's say, value of 3. But then, we'll create 10 threads. Thread, let's take reference, text, let's take the number that we're called with. Come. Pass it here. So the thread will do sem1.wait. Just wait on the semaphore to be signaled. Let's actually put this there. Build and print the number it was given, and exit. That's it, right? So we create 10 of those, but the semaphore is is a value of 3. Let's do detach these threads, and then somewhere else, I less than 7. We know that there will be 7 threads left. So let's now slowly let's sleep for 1 second, and then post. And now let's notify, let's increase, bump the semaphore by 1. And let's sleep 1 second, so you get to see all those threads finish. Okay, so now we have a semaphore. What should happen is the first 3 threads will get past this semaphore, and it will decrement it to 2, 1, and eventually to 0. And then the 4th thread will be blocked on this way. So we should initially see this program print 1, 2, 3, possibly, depending on how these threads are started and who gets there first. And then every second, we will unblock 1 more thread. So let's see. Let's see if this works. Well, that's not good. 1, 2, 3. Yeah, that's not what okay. I know. Hold on. See out. Flush. Nope. There was no new line being printed. So it was printing, but the console was buffering it, I think. So now if I force it to flush, there, 201, then 3, 5, 4. You see, slowly, 1 by 1, they are woken up. There. Let's see, do we get all 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There. So 10 threads were eventually unblocked. And we can verify that this works. Let's say we'll do, we'll notify 2 at a time. Space here. So now, again, the first 3 threads will get to it immediately. And then every iteration of this loop, we will wake up 2 threads instead of just 1. So we will see 2 numbers show up simultaneously. There. And of course, they're kind of printing all over each other. But you see that these numbers will always be between 0 and 9. So this isn't actually 23. It's just 2 threads printing their own numbers. Maybe if I get rid of this, it should be clearer to see. So there, first, and then 2 at a time. There, and finally, the last one. Right, since we unblocked 2 initially, or 3, so let's put it at 2. And then, right, there will be 8 left, but we're unblocking 2 at a time, so we can divide it. Okay, and then 2 at a time. And that's it. So that is a semaphore. Again, simple. Not sure about this refactor here. It's not very clean, so let's just keep it the way it was before. This way, we're guaranteed that post without arguments will always increment by 1. Again, some sort of a check here would be sensible. Count, no std, valid arguments. Don't be silly. There. Yeah. Beautiful. And you see that the numbers that the program prints, they're different each time because of the scheduling, the timing. So I'm starting 10 threads, but it's not always the thread 0 and 1 or the first 2 threads, right? That gets to get past the semaphore. Now it's threads first and third. Now it was the third first and then first, so on. So just the way scheduling is. Most likely the creation going through this loop is very quick, and these 10 threads are created. Operating system picks it up, starts scheduling it, and this is a machine with 4 cores and hyperthreads, so eight logical cores, I suppose. So how they get to be scheduled is completely random, as far as I can tell. Okay, so these are the multi-threading primitives I wanted to cover today. Show you how they're built, how you can using very simple atomics build your way up into more complex synchronization primitives.